So first let me say very quickly what is the content of the talk. So we have a proper map between toric varieties. To give this is the same as giving a map between the underlying fans. Sorry?
There's a category of toric varieties, like toric maps, right?
Yes, yeah, I'll say a bit more precise later, but yes. And of course, the set of cones in this fan is a poset. The set of cones in this fan is a poset, so there's a map of posets here. So the goal is to look at a map of posets and extract the topological information about the map F. Well, if you state it like this, it's kind of tautological that there should be an answer, right? So the point of the talk is to make this answer explicit. So first, let me just say what I mean by toric variety. So a toric variety X. So I work over the complex numbers, but everything holds over any field. And I work with cohomology, with Q coefficients, and same for the intersection cohomology. So a toric variety is a normal variety of some dimension n, with an action of a torus of the same dimension with a dense orbit. Now, given this definition, you work and you extract from it a lattice inside of some Euclidean vector space and a collection of cones. We call this a fan. With the property that all the faces of every cone in the collection are cones of the collection. So, of course, here the example of the affine plane. This is supposed to be the simplex in R2. You can blow this up. There's a map of the corresponding cones, or you can embed it. Which also corresponds to a map of the corresponding fans. So now to give a singular example, let me take just this picture over here. This is supposed to be in R3. This is just a square. I take the cone over the square, And this corresponds to the cone, the affine cone, over P1 cross P1 inside of P3. The difference between these pictures and this picture is that here all the cones are simplicial, and this is obviously not simplicial. And these are smooth, and this is singular. Okay, so the first thing I want to say is that I want to tell you what I mean by combinatorial. I want to say when an invariant is combinatorial. So by definition, to me, that means that it only depends on the graded poset of the fan. So the fan is also graded by the dimension of the cones. So now it's known that if X is a toric variety but it's singular, then the Betti numbers are not combinatorial.
So graded means you keep track of the dimension
of each cone, yes. So there are explicit examples of X projective, toric singular, where the Betti numbers are not combinatorial. On the other hand, it's a theorem that if X is projective toric singular, so any projective toric variety, in fact, any complete singular or not, then the intersection Betti numbers, so the ranks of the intersection cohomology groups, are combinatorial. So from the point of view of that problem, it looks like we have to give up on cohomology. Yes, but in the arbitrary case, then. So in fact, that's the next point. So first of all, the point I want to make is that we're going to work with intersection cohomology. Sure, sure.
But also if it's simplicial, it could still be.
Yes, yes, but
Then
yes,
it's okay. You could build
yes,
that in with smooth, right?
yes. But if it's singular,
It's still singular.
I know. But if it's singular in general, it's not true,
Yeah,
right? So.
yeah, okay. So you use singular to mean not simplicial.
It's not if and only if.
Yeah, I know.
So it's not combinatorial, period, in general. So this means that I have to abandon intersection, I have to abandon cohomology, I have to look at this as the invariant to look at. Okay, so Patrick makes a point. So let's say what's behind the smooth picture, in fact, the simplicial picture. So, so this is a warm-up fact. So if X is a compact, toric, and smooth, or simplicial, then its cohomology, which is also its intersection cohomology, is even, so in odd degree 0. It's pure. It's Hodge state, so everything is PP. And it's combinatorial. In fact, we have a formula for the Betti numbers. Let's remember this. Which looks like this. dl is the number of cones of codimension L in the fan. So you look at the fan, you know the Betti numbers. So the Euler number is D0. In fact, it's easy to prove this if you know enough. So let's give a sketch. So by Hodge theory, the cohomology is pure. Now, mixed Hodge theory, on the other hand, gives you the Hodge-Deligne polynomial. Now, it's well known that you can now go from the Hodge-Deligne polynomial to the Betti numbers due to cancellations. However, when you have purity, you can do it. So the first thing is that in general, regardless of purity, this polynomial, given the fact that X is a union of orbits, so it's a union of tori, using the scissors congruences, this is just the sum of uv minus 1 to the codimension of sigma, sum over the sigmas. So this is regardless of compactness, smoothness, and whatever. But now, because it's pure, you combine the two facts, so purity plus a special form of Hodge-Deligne polynomial. You get, by purity, you get that E of TT is the alternating sum of the Betti numbers. And so you get that this alternating sum of Betti numbers, according to that formula, is this. So you get all three propositions. Okay, so now let me say briefly what a toric map is. This is a map that, so if I have toric varieties, a toric map, given the fact that you have the torus inside of X and the torus inside of Y, if we're given a map of tori, a toric map is a map that extends the map of tori. So if it exists, it's unique, and it's automatically equivariant. So once you have this definition, this is the same. A toric map is the same as giving a map of the underlying fans. By this I mean that the lattice goes to the lattice, and each cone in here is mapped into a cone in here. Means inside, not exactly onto. So for one example and one counterexample. So this is the picture for the Hirzebruch surface. The Hirzebruch surface maps onto P1. So this is an OK map. But this map of sets, which suggests there should be another projection onto P1, is not giving rise to an actual map because this guy doesn't go inside of a cone. So this gives rise to the usual projection of the Hirzebruch surface onto P1, and this map doesn't exist. So now I want to give a key example that explains what I'm aiming for. And I want to take the blow-up of the affine plane. In some sense, everything is already there. Okay, so this is the picture for the blow-up of A2. So the exceptional fiber is, of course, a P1 with its two fixed points. And we have three simple facts. The cohomology of the exceptional fiber, it's even, pure, PP, and combinatorial. In fact, for this fiber, you have that the zero Betti number is the difference between the codimension 0 cones upstairs and the codimension 1 cones upstairs that go to this cone over here. So 2 minus 1. And the second Betti number is the number of 1 cones. So the formula is combinatorial. 2, the direct image, let me use the intersection complex, even if the intersection complex is the constant sheaf, splits into the intersection complex. Everything here is smooth, so this is redundant, but it's useful for later. Into the closure of the dense orbit, direct sum,
Sorry, DI is the number of I-dimensional cones?
codimension. Yes. Remember, this is A2, and this is the origin. So we have the splitting. And third, this is more or less the essential point that will come up later. We can build an invariant out of this picture. In this case, it looks artificial, but in fact is the answer to the general problem. So let me define P omega to be the dimension of the cohomology of the fiber over the generic point. Remember, omega is the 0 cone. It corresponds to the dense orbit. The dense orbit has a distinguished point. And I take the fiber over that, and I take its total dimension. Then I define, so I want to define an invariant for each cone downstairs. I define P lambda 1 to be the dimension of the same thing, but over the generic point of the corresponding orbit. And then I subtract, let me define, after I define P omega, I define delta omega to be P omega. Let me define this minus P omega. I do the same for P lambda 2. And finally, I define P rho to be the dimension of the exceptional fiber. Minus delta lambda 1 minus delta lambda 2 minus delta omega. So the general form will be that I take these cohomologies, and for every cone, I inductively define delta sigma to be P sigma minus the sum of the deltas that come before it. Let me see. Yes, thank you. Thank you. So this is the invariant. Now, in this example, you can see that delta is 1 here, 0 here, 0 here, and 1 here. So first of all, delta is always positive, which is not clear from the definition. And secondly, is positive, strictly positive, if and only if the corresponding orbit appears here. So let me say it again. That's right. That's right, yes. We have to take into account the singularity, so we have to give the right definition of delta, but that's all that there is to it, yes. So the point is that these facts 1, 2, 3 generalize to any proper toric map. So that's the content. This is how the first preliminary form of the answer to this. Now, I said why we need to consider intersection cohomology, because it's a combinatorial invariant. Now, why proper maps? Well, if you start deleting these cones, you destroy the properness of the map. And then if you check 1, 2, and 3, they all fail. So there is no hope, in my knowledge, to obtain any reasonable result without the properness, at least in this direction. So this is why we look at proper maps, and this is why we look at intersection cohomology. Okay. So first I want to start discussing our approach to this problem. So first of all, we want to make a reduction to a case that it's easier to analyze. And then we will make a second further reduction. So let me go in steps. So I want to look at toric fibrations. So a toric fibration by definition it's a toric map which is proper, which is surjective, and has connected fibers. So in positive characteristic, you have to change the definition, but at the end, it doesn't matter. The results are the same with this other natural definition.
What do you do?
Well, this is not enough due to Frobenius, right? So you just take that the map of the underlying lattices is surjective. So the first fact is that you have Stein factorizations in the toric world. So this is a definition. So now take any proper map of toric varieties and then Stein factorize Yeah, sure. Sorry? Say it again?
You have something that has the first three properties, but not the last. Can't think of anything that could possibly have that. Maybe
The square map.
But it's not toric, right?
What do you mean it's not toric? T to T square.
You have any homomorphism of lattices?
T to T square.
Oh, sorry.
No, good. Well, why sorry? Okay. In positive characteristic, it's worse because, you can have this. And okay. So now the fact is that you prove that, first of all, this is in the toric world. So this doesn't come out of the definitions, but you can prove it. So now what happens is that you have here a toric fibration and here a finite map. So remember, my interest is in the direct image of the intersection complex for F and in these cohomology groups. Because they are the stalks of this. So if this is my interest, then I claim it's enough to study fibrations. Because if you take a finite map, the irreducible components of the fibers of this are just the fibers of this. So if I'm interested in this, it's enough to look at this. Makes sense? So if I'm interested in this, it's enough to look at these. Now what about this? Well, as I will discuss in a second, I'm interested in how this splits. So because this is a finite map, a splitting here is reflected here automatically. So what I mean by that is this. So one, the connected components of the fibers are fibers of F, of G. And two, a direct summand, no, all direct summands, so direct summands of Rg lower star. So if I push forward first here, because this map is finite, they correspond to direct summands via the ordinary push forward. So if I understand this, I understand this, at least from the point of view of what I'm interested in. So from now on, I only take toric fibrations. Q coefficients.
Then that splitting, like, if you do that, it seems like if you do like x goes to x cubed if you want, right? Then that thing will split up.
Well, but it's the direct image of the constant intersection C is the intersection C with coefficients in that local system. So I'm not saying that they're constant. I'm
You're
just,
not making it split up.
but it's still how do you say it? It's still a semi-simple IC.
But you don't split it into 3 rank 1.
Well, you can do that further, but the point is that the ICs supported on some varieties, they are in bijections. The coefficients, of course, are also in bijection like this, but then down you can split further. But that's not unexpected. That's the way it should be. By the way, in this special toric world, well, I'll get to that later. So we reduced to toric fibration. So now we are looking at F fibration, toric fibration. So now let's zoom in more precisely on this problem. So then after I explain what is that I want to look for, I can make the second reduction where I take a fibration onto a very special toric variety, which is affine and contractible. I'll do that later. First, let me give a definition. So a complex of sheaves on X, constructible, is semi-simple if it's a direct sum of shifted intersection complexes. with twisted coefficients, which are semi-simple. So this is the decomposition theorem, and it's due to Benenson, Bernstein, Deligne, and Gaber when the coefficients are of geometric origin. For example, the constant sheaf, that's already a deep theorem in that case. Due to Saito when the coefficients are polarizable variations of pure Hodge structures, and in complete generality due to Mochizuki, which proved the case where there's apparently no geometry whatsoever, just semi-simple local systems, but the theorem holds anyway. Really amazing. So if F is a proper map between complex varieties, then the direct image of a semi-simple is semi-simple. So for proper toric varieties, we want to ask, what are the pieces of this? Okay, one of the remarkable consequences of this theorem is that this complex is understood. This complex is given to you, how do I say this? The splitting of the complex is Zariski local on the base. So its splitting is Zariski local on the base. Now let's stop. What does it mean? It means that if I have a covering given by two open sets, and I find a splitting here, and I find a splitting here, then I should be able to combine the splitting into a splitting over the whole thing. Now don't take this for granted, because it's false for the projection of the Hopf surface onto the sphere. So in complex geometry, it's false. It's true only in algebraic geometry. So this statement is very strong, and it's consequences of this theorem. So this means that I can work on a Zariski open cover of the target. So first of all, there's an obvious Zariski open cover of the target given by the U sigmas. Let me tell you what they are. So U sigma is the union of the orbits with this property. I take sigma and all its faces, and I take all the orbits. They combine together nicely to give you a toric affine variety. So I need to understand, I take the situation from here to here. And to understand my issue, it's enough to understand that over each open U sigma. But now the U sigmas have a local structure that allows me to make a further reduction. U sigma equivariantly looks like the orbit sigma times another toric affine variety of type U sigma prime, where U sigma prime is affine toric, and it's given by the fan associated with sigma, but not viewed in the original lattice, but sigma viewed in the lattice spanned by sigma. This lattice has lower rank. The rank is the dimension of sigma. So this is a smaller dimensional variety, and this is your local product reduction of U sigma into a product. But now the thing that is important to us, well, two things. RF lower star IC X U sigma, remember this is what I want to study now, because of this formula, is canonically isomorphic to the projection, pull back under the projection onto the factor of, well, I went ahead of myself, sorry. Okay, so this is the first thing to say. This is not just a fine toric, but it also has a unique fixed point. And there's an equivariant embedding inside of some affine space with respect to a torus action with positive weights. So everything goes to the origin, and U sigma prime goes with it. So I call these toric varieties of contractible type. So the abstract definition is an affine toric a toric varieties of contractible type if is toric, affine, unique fixed point. Okay. Now the second reduction, remember now I reduce to this one. I want to reduce to this one. How do I do that? There's a second local triviality assertion. The map also factors over the splitting of the base. So if I take the per-image, this is a toric variety, locally factor through this orbit, which is just a C star to some power, and it gives me exactly this. And the isomorphism is compatible with the original map. That gives me a new map, and the advantage is that now this is of contractible type. So this is a fibration, toric fibration over contractible. What's the advantage? Is that the RF lower star of ICX U sigma is the pullback via the projection. For this one. So this is my reduction using the local triviality. So it's enough to study these. Okay, so now let's study these. Fibration onto contractible and purity theorem. So let F be a toric fibration onto Y contractible. Then the intersection cohomology of X is pure, is even, is Hodge state, and is combinatorial. So this is the first result. Now, if this is a point, this is exactly the theorem I mentioned before. So the theorem is that nothing changes if you replace the point with a contractible toric variety. Corollary B, let F from X to Y be any proper toric variety. Then for every point in the image, this group is pure, even, Hodge state, and combinatorial. Now the corollary is immediate via the Stein factorization. So you apply theorem A to the Stein factorization, to the fibration G, and you obtain the corollary. So it's an immediate consequence of theorem A. Now the proof of theorem A is relatively simple. In fact, there are many. Let me give you one that is maybe not very direct, but is very quick. So this is my x, this is my y, which is contractible. And I have some fiber over it. Now the hypotheses of the fibrations say that the lattices surject. That means you can split the surjection. This means, first of all, in general, ICX is a torus equivariant. What does it mean? It means that if I take the map from x times the torus to x, the action, and then I take the projection, then something is torus equivariant if act star is the same as per star. So the intersection complex is torus equivariant. I should say this is not the real definition because I'm omitting the cocycle condition. So maybe you call it torus weakly equivariant, whatever. But for this talk, I call it like this. Now, because of the splitting, you can prove that RF lower star ICX is TY equivariant. Now, the base is contractible. So there is a canonical isomorphing via the contraction of the cohomology group of X with the cohomology of the fiber with coefficients in the ICX. Now there are some shifts involved, which I omit discussing. But there's a canonical isomorphism here. Now, because X is open, its weights are greater than or equal than star. Because the fiber is closed, by purity, its weights are less than or equal to star. No, this is intersection cohomology. Yeah. So the weights agree with the degree, so we have the purity.
Why is like the closed point? Why is the closed one? Why is the special point? Right?
Yes. So intuitively, imagine that everything retracts onto the central fiber.
So you took a different point, wouldn't be true.
No, of course not. No, it has to be contractible. When you contract something, the point to which you contract is important. Okay, so you have the purity. Now, this and this followed by the same argument in the warm-up argument. You take the Hodgson polynomial and repeat. Now, the combinatorial argument, the fact that it's combinatorial is, in fact, you get the same formula as before. Actually, no, sorry. Let me correct that. That formula was under the assumption that x was smooth. So let's say that x is smooth. Then you get the same formula as before. If x is singular, you just prove that this is combinatorial in the sense that it depends only on the poset. Okay, so this proves theorem A.
Somehow depends on the poset of X, but also the poset of Y.
It has to, right? Because it's because here you have you picked a fiber, and then you're taking the coefficients upstairs, and the point is downstairs. So things are intertwined. maybe this is clear if x and y are smooth. The same formula holds, but the meaning of the terms is different. So let's say that your contractible variety has this unique cone sigma, which corresponds to the fixed point. Then dl sigma now are the cones upstairs of codimension L that map into sigma. So now you see how the two posets are interacting to give you the formula. Okay. Now, if you ask anybody, they would say that this statement, purity and being even and on state, should be true a priori. Why? Because you can prove that the fibers are always union of orbits. In fact, they are union of closed orbits. Each orbit is a toric variety. Each toric variety has this property, so this union should have the property. But there are two catching problems here. First of all, it's not cohomology, it's intersection cohomology. But let's say that X is smooth, so this is cohomology. Then you know that the components are toric varieties, but you don't know how they meet. So you cannot, at least I can't directly, looking at the fan, tell you, I look at the fan and I know that the configuration doesn't have cycles. Because this is what you get from the theorem.
Why wasn't contractible?
No, they're all true. Sorry, this is true regardless of the base.
No, but then you said that
Well, no. I mean, if you take C star onto a point, it's not true. Yes. Yes. By the way, this is my ignorance. This is not really my field. But if the variety is not compact, I don't know, even if it's smooth, I don't know a formula for the Betti numbers. Okay, but that may be very well known. It's just not known to me. So if you leave the world of proper maps, I don't have general answers to anything. Okay, so theorem C, the decomposition theorem for proper toric maps. I only give the statement for fibrations, because otherwise I have to introduce more notation. So for a fibration, the direct image of the intersection complex of X is isomorphic to the direct sum over the cones, direct sum over the integers, or intersection complex of closed orbits with suitable coefficients and twists, shifts. So also this, I think everybody would expect to be true. Additional information. So first of all, of course, here you could have something with exponent 0. So the supports of F are by definition those V sigmas that actually appear in the direct sum decomposition. So they're actually there as direct summands. Remember, in the example of the blow-up of the affine plane, I only had 2 of these. The cone given by the origin and the cone given by the biggest cell. Now, Poincaré-Verdier duality tells me that S sigma minus B is S sigma B. This evenness statement tells me that there is a vanishing when something is odd, which I don't write down. And then if F is projective, you have the relative Harlesh's theorem. So for every sigma, for every B and L integers greater than or equal to 0, these S are monotonic. In this sense. Now, let me just say a few words about the proof. So these are all easy consequences of the facts I put in parentheses, provided you have this. So how do you get this? Well, I repeat that equivariant argument from before. This is so I take a fibration. That means I can split the surjection of lattices. That means that when I push forward this, I find something equivariant on the base. Because I have the decomposition theorem of Benison, Bernstein, Delisle, and Gaber, every summand, you can check, must be equivariant. And so it's an intersection complex supported on the orbits, on the closures of the orbits. But now you could have twisted coefficients. Now, in general, it does. But actually, you can say exactly what they are. That's a different discussion. But in this case of a fibration, the coefficients are constant. And that's because of the local product formula. Okay, so I don't discuss this further, but it's really easy. So that's all that there is to it. Very simple. Now, I repackage this to give an answer to the original question, extracting information about the relation between the intersection cohomology of the variety and of the fibers. Probably yes, but I don't know how to do it. I think there are these techniques of using sheaves on combinatorial objects, and I don't know, I don't think there is any such result, but maybe one could use that technique. For example, there are results in the Harlesh's direction, but I don't know if there are results in this direction. I just don't know. Okay, so now I want to give an answer. So remember that in the example I defined of the blow-up of C2 at the origin, I defined some invariant P sigma as the total dimension of the cohomology of the fibers. Now that's too naive because it does not take into account the singularities at the target and at the source. So I need a modified definition. And that, what I said in that example, generalizes in complete generality. So the first thing is that I want to consider these numbers. Now remember that if I have this relation, I have my closed orbit that contains the closed orbit of sigma, that contains the orbit, that contains the point, the distinguished point of the orbit. So I want to define this number as the dimension of the cohomology sheaves of the intersection complex of V tau at this point. Now, if y is smooth, this number is typically 1. If y is singular, it encodes some aspects of the singularity of the toric variety. So first invariant, second invariant. This is on the base. This is for the fiber. I take this invariant. Instead of the cohomology of the fiber, I take the cohomology of the fiber with coefficients in the intersection complex of the source. then I define my invariant delta sigma to be p sigma minus the sum over the taus less than sigma of r tau sigma p tau. No, delta tau. So this is a inductive definition that starts with the cone 0, called omega earlier, where this is defined to be this number for the generic fiber. So now I have this sum, this construction, this invariant. And note that these terms are positive, these are positive, but it's not clear that these are positive, and moreover there are these minus signs. So, okay, so now we can repackage the decomposition theorem in this theorem. First of all, this is not a consequence of the decomposition theorem. It requires further work. But the p sigma are combinatorial. Delta sigma equals the sum of the sigma S sigma b, the exponents in the decomposition theorem. So in particular, it's semi-positive, which was not clear from here. And second, delta sigma is positive if and only if b sigma is a support. It actually appears in the decomposition theorem through its intersection complex with some exponent and some shift. Now, of course, this is just a repackaging of the decomposition theorem using those definitions. But now there is also a further statement that makes it clear that this is also combinatorial. So you can prove that this is combinatorial. But according to this definition, I would like to prove that this is combinatorial according to this definition. So there's a further formula. Where instead of taking this invariance R, which comes from the intersection complex, I take the function R. This function belongs to a certain algebra called the incidence algebra of the poset on Y. This is a combinatorial gadget that you can read about in Rota's manual of combinatorics. In that incidence algebra, you can talk about inverses. This is the inverse to R. So it's completely combinatorial, extractable from the poset and the function R. In a special case, it's called the Möbius function. That's the Möbius function when Y is smooth. In this case, it's what it is. But it's clear that this is combinatorial according to this. It's clear that this is combinatorial because it's the inverse of a combinatorial object within this incidence algebra, which is combinatorial. And so this is the... Okay, so now let me conclude with a question. I would like to know if there is a direct combinatorial argument for the semi-positivity of delta, because we use the decomposition theorem here. So in dimension 3, there is a nice answer, but we don't know beyond that. If I take a simplicial complex in dimension, simplicial cone in dimension 3, and I take its fan, no matter how I refine it, which corresponds geometrically to a proper birational map onto C3. So no matter how I refine it, I will find that the invariant for sigma is 2 times the number of rays in delta prime interior to sigma. So for example, if this is my picture for C3, so the cone over this, if I blow up a line, I get this. There are no rays which are interior, because the rays are one-dimensional objects, and this is two-dimensional. But if I blow up the origin, I get this picture, and I get one ray, and I get two here. So by looking at the picture, I know if the origin contributes a summand or not. But I don't know of any such formula in higher dimension. Okay, so it's time to stop.